Okay, so let's begin this round of system design interview. And here I will design. So let's say I'm sitting with an interviewer. And so the question is design a URL shortener like bit.ly. Yeah, so here's my question, right? So design a URL shortener like bit.ly. So that's what I have to do now. Yeah, so let's talk about it, right? So beginning with some questions, so that I would have for the interviewer. So what does this product do? Like, what does this software do? Basically it takes in a short URL and then converts a long URL. If you've ever used TinyURL.cc, that's what like this is, right? Okay. And then, the next thing I do want to ask you, like, should we have a custom alias? So should we provide a custom alias to the user? So, sometimes they might not want a random string to be generated. They want a custom alias. Yes, you can provide them with that. Okay. And then do we give them the option to expire the links? So do the links expire? Yeah, so uh, if unused for 30 days, they expire automatically. Okay, so they do expire automatically. Otherwise, user can explicitly mention an expiry date. So there's these both ways that um, expiration will work. Okay. Um, sure. So yeah, like moving on. So some of the other things that come to my mind is, um, do we want to build analytics? Do we want to provide analytics? So yes, we want to store analytics, but right now we're not exposing it. It could be a product feature that we offer in the future. Okay. Uh, like we could offer it to premium users later. Okay. Uh, yeah, it's good to think about that. And so, some of the other things that come to my mind are, yeah, what kind of scale are we looking at? Yeah, so let's say we have 10 million users daily, out of which, 10% shorten URLs, right? Okay, so that's the scale that we're operating at. Okay. So we have 10 million users daily, and so 10% of them are like actually using it to shorten. Cool. Uh, yeah, and so what are the other things that come to my mind are, yeah, and I guess the long URL can be of any length, like it can be really, really long, right? Yeah, the long URL can be as long as you want. Okay, okay. Well, I'm clear on, so based on some of the information that I've gathered, and let me prepare some requirements for our product, and there might be like I might have to circle back and ask you more questions as we go along. So functional requirements, user gives a short URL. Uh, the user gives the long URL, and we return, and the service gives them a short one for and the service gives them for a short one. User can request custom alias, if available, and then user can provide expiry of the short URL. Okay. And then another one will be unused URLs expire after 30 days of inactivity. So short URLs expire for 30 days of inactivity. And then we do want to store some kind of analytics. Yeah, and the last thing will be user gives short URL, and then they're redirected to the long URL slash original path. Yeah. So yeah, these are some of the requirements, right? Functional requirements. So these are some of the things that our system should be thinking about. Um, and then here, our scope, or I should mention that at the end. So I will also mention outer scope for now is exposing the analytics to the user. Uh, okay. So now let's talk about non-functional requirements, right? So latency is a big one, right? So writes should be within like 2 seconds, within a second. And then at the same time, like reads should be within milliseconds. Yeah, and so I would say read should be within 500 milliseconds. So yeah, we should be able to write within a second, and then read should be within 500 milliseconds. So low latency for our system, like that's what we want. At the same time, talking about scale, like we should be able to scale the system well, because there could be scenarios where we hit more than 10 million daily users. So let's say, because this is very common on Twitter. Somebody would want to post a URL, and somebody shortens the URL, they post it on their social media, and suddenly it becomes viral. And so we get a lot more hits then. So it could happen that we have a surge from 10 million to 50 million or 30 million users. So the system should be able to scale the system well upon surge of traffic. So let's say 50 million users. Yeah, on a surge on per day, at a surge. And then I would also consider, so we have latency. Yeah, at this point, I want to talk about like the cap theorem. So at this point, I want to, discuss about, and so our system should be high availability, um, which means that, the system should be responsive. And so at this point, system should be responsive at all times. And so at this point, I do want to cover the cap theorem, which is to say that, given a distributed system, which is to say that given a distributed system, we can get two of these three, so we can get two of three characteristics, which is basically consistency, availability, and partition. So yeah, and so given this is a distributed system, we have to accept that we will have partitions, like some or the other servers, databases, caches will fail, and so we essentially have a choice between consistency and availability. So between high consistency and so between strong consistency and high availability. And so in this case, since we want our users, So let's say a user creates a URL, and they don't instantly go and hit that tiny URL. It takes a little bit of time, like before they actually go hit it, before they actually share it with someone else. So I guess like consistency is less of a concern than availability. Like every time our user is trying to create a short URL, we should be able to return it to them. At the same time, every time there's an access to a URL, like we should actually show them something or the other. So, availability is what I'm prioritizing over consistency. And so these become our non-functional requirements for this. And then our scope is like right now we're not exposing the analytics to the user. That is totally out of scope. And if we do have some time, like I will circle back to that, right? So these are some of the requirements of our system. Um, and then talking about the core entities, right? So they're basically the URL, which is like the short URL, and then the long URL. Those are two of our core entities, and then the user is our core entity, which has like user ID, etc., etc. And so with the URL itself, we have short URL, long URL, creation time, expiration time. So pretty much like that's it, right? So the user can give expiration time and they have a creation time. Um, yeah, and so those are some of our core entities, right? And so I will also talk about yeah. So yeah, these are what I see as like our core entities. Um, yeah, if provided. So this one is optional. So the expiration time is optional, like the user can provide it or they can totally skip it. And then I guess one of the other things that we should have here is based on my system is like last accessed time. Yeah. So yeah, that is one more key detail that I want to have, like when it was last accessed. Uh, so those are pretty much my core entities. Like those are the two that I see. And let's talk about some API design. And so basically, which is to say that our users, as we discussed, like so, if we look at our functional requirements, the user gives a long URL, and the service returns a short one. So so they would send, and so let's use HTTP REST for for all the communication. So the users would send a post request to like post slash URLs, and then the request body will have a short URL, yeah, and then an optional expiration time, and I guess an optional custom alias. That is also something they can provide. Um, yeah, so pretty much this will be a request body, like short and simple. And then this expiration time is like optional, right? And then this custom alias as well is optional here. So yeah, so the user, maybe they provide it, maybe they don't provide it. Oh, I'm sorry, this is the long URL. So something like, linkedin.com slash Garang Rana slash ins slash time zone equal to ET slash something, 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 something. So this is what pretty much a long URL will look like. And so this is something that, a client might want to shorten. And so in response, the system returns a short URL. Basically. Yeah. So in response, the system returns a short URL. Returns 200 OK and a short URL, right? And so the second one would be, get slash long URL, or like get slash long. Yeah. So that's pretty much it. Like it could also be get URLs. And so in this case, the user will provide like a short URL, I mean, yeah, so they would send like a GET request uh, on, the short URL itself. Um, yeah, so it would be like Tiny.cc slash short URL or something like that. So whatever we, sent to the client, like they would just query that back. And so, yeah, so, and then we can also have v1s slash URLs, get tiny slash short URL. And so this should return the long URL or the original URL to the user. Yeah, and so pretty much that's it, right? So they do a 200, and so we return them uh, the long URL. Yeah, so yeah, talking about the status code here, so there are two status codes that we could return them, like 301 or 302. And then 301 is like a permanent redirect, um, and then 302 is like a temporary redirect. So the difference between both of them is, uh, yeah, so the difference between both of them is, so let's say, I return status code. Um, yeah, so let's say I return status code 301, which is like the permanent redirect. And so what happens there is, yeah, so what happens there is, yeah, so what happens in the permanent redirect is, you know, um, the browser saves that, the URL, and so the browser will save that URL, so it will know that this short URL redirects to this particular long URL, so it will save it, and so we will stop getting those requests. But at the same time, 302 temporary redirect just means that, we're redirecting the client as of this moment. And so every time they try to open the short URL, it would hit our backend servers. And so in this case, I would go ahead with the 302 um, uh, temporary redirect, and the reason is like it will give us analytics, and then we will also know the status of our production systems, like if we start getting any error, like we would know that something or the other is going on or something or the other is wrong. So that's what it's for, right? So yeah, that's pretty much it. Like get tiny.cc short URL, and then it returns um, yeah, long URL, or like 302 with long URL. Yeah, so that's pretty much our API design for this. Those are all the things that we need. And now let me just take a look, right? Analytics to be stored. Yeah. So I guess one of the things that I do want to talk about is analytics. And so we will dive into it like during our discussion of the system itself. Uh, And then, also just to roughly take an idea of the scale that we're at. So 10 million daily active users, out of which 10% write. So, that becomes 1 million writes per day. And so, looking at the long and the short URL, like a short URL would be just 7 bytes. So, uh, so we could easily say that everything would fit in 100 bytes, and and then we're doing 10 million 1 million bytes a day, which is 1 into 10 to the power 6, and so that becomes like 100 million bytes. So which basically becomes kilobytes, megabytes, and then kilobytes, megabytes. So that becomes 100 megabytes per day. And so, per month, that would be pretty much 300 megabytes. And then for the whole year, we could estimate it at like 1 gigabytes of data per year. So, the scale of our data is not that big. Even if I were to multiply the whole thing in five, like, if this was 500, that would not be a lot. Like 500 bytes into 1 million, so 10 to the power 6, which would be 300 kilobytes, megabytes, so 100, yeah, 500 megabytes into 30, like 1.5 gigabytes. Yeah, so that's not a lot, right? So our scale's pretty, like, this is like pretty low scale. So I don't see that we need more than, one single database. Um, so yeah, moving on from the scale, let's move on. Um, so these are like writes, and then we have 9 million daily active users, and so we have 10 million daily active users, and then in a day we have 10 to the power 5 seconds, and so basically that is like 100 requests per second. And then during a surge, we could peak this at like 250 requests per second. And so, modern day servers should be able to handle that pretty easily. Um, So yeah, modern databases and servers should be able to handle that pretty easily. And that should not be a problem here. So now let's talk about like, some of the systems that we will now design. So let's talk about the systems that we are going to design now. So yeah, so so let's enter the high level design now. So this is basically our user. So our user sitting here, and then they send a request to our API gateway. And so they send a request to, our gateway, and the gateway actually offers like a lot of things. And so basically just think of it as like a central door to our services. And so all the requests go from here. And then, we have a read service, we have a write service. Um, Right, and so we have read service, we have write service, and both are responsible for, some of the executions. And then we have a URL database, which has, the URL stored. And so this is what, our requests will look like. So the user sends a request to the API gateway. The API gateway then sends the request to the read service. It sends the request to the write service. And then both of them also talk to the database itself. Uh, so pretty much like, this will be, our, and so, right. And so this will be basically our, low level design. Like it's pretty easy. So the user sends a request. The request goes to the API gateway. And so the request that they send is, post slash URLs. And so when they're actually requesting the URL, like a short URL, this is the request that they send. And then once they want to retrieve, they actually send a get to the short URL. And so, we return a 301, and so they want to be redirected. And so those requests go to the read service. So it's pretty simple here. And so, yeah, let's talk about what happens, right? So let's talk about a user flow. Yeah, and before I dive into the user flow, I do want to keep like the URL table, and so basically this has an ID, and then it has a short URL, which is and then it has a long URL. So all the fields that I mentioned, like creation time, uh, and then expiration time, and then last used, last accessed. Right, and so these are some of the things that it has. Other than, we also have a users table, as I mentioned before. And so basically, this has the user ID and, some other metadata about the user. Um, right, and so this also has like some other data about metadata about the user. So now let's talk about what happens. Like, let's talk about a user flow specifically. So the user comes to our platform, the user wants to shorten a URL and they have a long URL. And so what happens is, they send a request. So they go to the UI, they say, okay, this is my long URL. Can you convert this to a short URL? And right now they're going just with the default parameters, like everything's default. So what happens is, that request goes to the write service. The write service basically, its job is to take that long URL and convert it to the short URL, right? And so right now, for now, let's say, it magically does that. So we will go into that into when we discuss the deep dive, but for now, let's say, it magically does that. It takes the long URL. Um, and then it goes to the database, it saves all of that information, right? So it saves the short URL, long URL, creation time, expiration time, and yeah, pretty much that's it. And the last access would be null in this case, and then we return the same to the user. And so in this case, I guess we should keep like an arrow head on this side as well. Oops. So yeah, we should keep an arrowhead here as well, and we should keep an arrowhead here as well, because these are bidirectional communications that are happening, and so same over here. Um, so yeah, and then we return that to the user. So the user now, let's say the user goes and he gives that to five of his friends, and so they all start querying with the same tiny URL that we generated for them, the short URL that we just generated for them. And so what will happen is all of those requests will go to the get short URL, and the get short URL would look at the read service, and so from the read service, it will look at the database. It will say, okay, what is the long URL based on the short URL? And so once it finds it, we will return it to the user. At the same time, like, when you're trying to find it, we should also check the expiration time if it has been set or not. If it is already set, then we pretty much just not return it, and so we return a 500 to them. Oh, so we return like a 400 to them, like bad request. Since the URL did not exist, we could also show them the error message that this URL does not exist. Um, at the same time, we will also update the last accessed. Um, so let me think about this. Do you want to update this right now or not? Actually, yeah, that's pretty much it. Like, that's what we do, right? So we check that the expiration time is not more than the current time, and then, we just return the long URL. So this pretty much will satisfy, our system. So this will work out of the box. And so just this system itself will satisfy all the functional requirements. Um, Let's see this. So the user can give a long URL and then get a short one. The users can request custom alias if available. Yeah. And so for that, what will happen is when, we are showing them the UI, the user can specify a custom alias. And so what will happen is, our write service, since this short URL, so it will use that alias as the short URL. And since this is the primary key, our database will error out the transaction if the key was not unique, and so we can pretty much show that to the user, and so we basically get that the uniqueness for free, since the alias cannot be non-unique. So we have to avoid collisions, and so the alias should be non-unique, and so our database will help us get that. In case, so the user provides an expiration time as well, so we pretty much just save that expiration time as well over here. So yeah, let's look at the functional requirements. So the user can give a long URL and we return a short one. The user can request custom alias if available. The user can provide expiry, yes. So the user gives a short URL and then they're redirected to the long one. And so we just discussed, the get request will go to the read service, check the database, return back. So that's pretty straightforward as well. So short URLs expire after 30 days of inactivity. And so to do that, what happens when we expire a URL? So do we delete this from the table or do we keep it in the table? Like that is something we should discuss. So because both will have different approaches, yeah. So, if we want to, so just to clean up this database, I would suggest having a cron job. Um, And so what happens is, this cron job looks at the database. So it runs every night. So it runs nightly, at a time when we don't hit too much traffic. So the cron job runs nightly and it just clears the database. So it looks at the expiration time. And so, it looks at the last access time. And so if this has to be deleted, like if, both one or the other requirements has been met, then it pretty much deletes, that URL entry from the table, like if the expiration time has reached or if it was last accessed 30 days ago. So the cron job actually will delete. So yeah, so so this will do delete from URL expiration time is greater than equal to current time. Uh, and or like last accessed is greater than equal to 30 days. So based on, this logic, it will delete from the database, and that's pretty simple. Like we could schedule this like nightly or monthly, whatever. Like that's pretty easy to do. And so, we could just pretty much run this monthly based on, the traffic. Like we could run this like weekly or monthly based on how we feel. Um, at the same time, I guess one of the other functional requirements was that the analytics should be stored. And so that's what I was coming to. And so that will also cover how we update the last access. So every time, the user, like every time somebody actually reads, so every time somebody reads from our database, our clients request that they didn't want to read the database. Yeah. So every time we get a read, statement from our database, what would happen is, yeah, so we send that event itself. So we send that event to a write-ahead log, right? So the user wanted a get, and what happens is, we keep a log here, and so this is pretty much a val. So this is pretty much like a write-ahead log. And so every time there is an access, like the read service is reading something, we just log it here, right? Oops. Yeah. And so in this case, it is a unidirectional arrow. And so, yeah, so that's what happens here. It logs. That's as simple as that. So every time, there is a read, we log it. Every time there's a write, we log it. So even like, our writes are logged as well. Yeah, and so here we go. And then same for the write service as well. Like it just every time, somebody writes, like we just send that message to a write ahead log. And so it's pretty much just dumping the stuff. So it's pretty much just dumping in the log itself. And so, it's pretty quick, it's efficient. And so at the end of the day, we will have some jobs. So maybe we could have Spark run, and like since our load is pretty light, like we could just write a script to do this, or we could have like a Spark that's run. And so this one is run nightly. And so basically what it does, it looks at the log, and it accumulates all the analytics that we want. So it stores all the analytics. So everything is stored in the val, and so we can pretty much just generate analytics from this if we want to, or we could use this to store it in a database. Like from the write ahead log, we this could copy it inside a database, right? And so we could have analytics DB. And for this, a time series, and for analytics DB, like, we don't need to have like, a SQL sort of database like we could have for analytics. It will be better to have a time series database or ClickHouse, which is basically meant for analytics sort of queries here. Yeah. And so this is it. And so the cron job actually reads from the write ahead log, and then, it actually enters everything inside the analytics DB. And so this becomes pretty easy to manage here. Yeah, and so this is how we keep our analytics. At the same time, Val and the cron job that runs nightly also updates our last accessed field. And so what happens it is that it looks at the write ahead log. It sees, everything that's happening. So it sees that, so and so URL was read, so and so URL was read again. So let's say facebook.com/ a particular URL from Facebook, or like a short URL was read 100 times. So, Val would take the last time period of that day and update the last accessed within the URL table. And so that is something that, this cron job and val are especially helpful for. And so we could also replay the events if we need to. And so we could have a 7-day retention here using the write ahead log. And so for write ahead logs, we could use Kafka. That's a good form of write ahead log. Or we could use like a RabbitMQ. Yeah, for write ahead log, we use RabbitMQ, right? Yeah. Okay, so moving on. So, that satisfies all of our functional requirements. Now moving on to latency, or sorry, like our low level requirements, so let's move on to the deep dive, right? So, the first non-functional requirements is latency, right? So a write should be within 1 second, and then a read should be within 500 milliseconds. So let's look at both of these, yeah? And so let's talk about the reads first, right? So I can clearly see an optimization that, we should have, a level of optimization that we should have is, the URL. like every single read is being sent to the URL database. So, the read service is reading from the URL database. And so, even though that is pretty fast, and we will get into why and how, I think like the first and primary need is to have a cache, and then the read service be able to talk to the cache itself. And so, let's look at so yeah, let's modify that. Yeah, so let's modify that. And so let's say we have a Redis cache or like a memcached. So we could have either of those solutions. And so what's going to happen is, my read service will then send a request to the cache. And so if this cache has the long URL, and so we would just return it to the user right then and there. And so also I do want to say that for the cache, I want to use a cache aside least recently used sort of mechanism. And so what's going to happen is, our client is our priority. And so let's say the user, reaches out to the read service. And so the read service checks the cache and that entry is not present. So it will check the database and return the URL to the user. At the same time, after it has returned the value to the user, it's going to write that same value inside the cache. And so that's what I mean by a cache aside strategy. And then the least recently used is basically just to say that, the URLs that haven't been used in a while. So, at some point our cache is going to it's going to get full based on our load. Like at some point, like our cache will, have less storage, and so there will be disk pressure. And so in those cases, what will happen is we will have a least recently used method, and so that entry or that short slash long URL will be kicked out of the cache, the ones that were least recently used. And so that's what this means. At the same time, let's also talk about, the reads. Like, so not every read will go through the cache. There are a lot of reads that will happen on the database. And so, if we have a SQL or a Postgres database, then, and our primary key is the short URL, like this becomes pretty simple, because, the SQL database, it does maintain all of this as B trees, which is like a self-balancing tree. And so the short URL itself, the lookup for the short URL will be log of n at all times. And so, the, the the database does not look through the entire table. It holds the location of that short URL in the memory, or sorry, of the short URL in the memory. And so, with one memory access, it would know exactly where to look within the disk. And so it goes to that disk location. It, looks at that specific subtree within the B tree, and then it finds that long URL and it returns that to the user. So that itself is fairly quick, and so that's log n time. And given that we also have a cache, we will serve a lot of entries from the cache, and so this will just work out pretty well for us. And then, yeah, so the writes should be fast. And so we did not talk about the writes yet. Yes. So how does this short URL get translated to, sorry, the long URL get translated to a short URL? And so, yeah, now would be a good time to discuss that. So there are a few approaches, this write service could have, that we could take for the write service. And so let's talk about some of them, right? So, the approach first approach that comes to my mind is, so a hash function. So basically, what happens is, we take the long URL, right? And so we apply a hash function. Let's represent that by fx. And so this yields us a short URL or like a hashed URL. And so, for hash, we could use something like an MD5. We could use a SHA-256, some or the other sort of hash we could use. So basically, this would just work out. And so let's talk about various different scenarios that would come up here, right? So, the hash could be, it could be like 25 characters long, but then it doesn't become short, right? So what we could do is, we could strip off the first 7 characters from the hash, strip 7 chars from the hash, return in short URL. And so what will happen is, there will be collisions. So let's say we hash something, and so we are getting like 1 million daily writes, so which increases the chances of collision. And so what would happen here is, the write service would check the URL database to see if this short URL already exists within database, and so we will have an extra hop every single time. And also, if we hash it, the hash is 25 characters long, and we strip the first 7 characters. So it is like there could totally be a scenario where we actually have more collisions. And so we could have a lot of collisions here. And so, there are ways around on how to solve the collision, which is basically what I told you. You go check um, the database, and so if there is a collision, you generate again. There is another one which is like so. Prefix with string, prefix the URL recursively with a string, and then hash for collision to avoid collision. And so what this means is, so if you have 2 URLs, and then they have the first few characters of their hash are the same, and so what would essentially happen is you would actually um, merge a predetermined string. So maybe you could merge tiny URL, and then you could hash it again, and so on and so forth, until like you avoid the collision. And so this will actually work out that way. But then there is another approach that we should talk about, and so that approach is basically, I think that is a better approach, and so which is base 62 encoding of so base 62 encoding of the URL. Uh, and so what happens in this case is, you generate an ID, and so, which is like a number. And so after you generate the number, base 62 encode it. Which is basically to say, so base 62 would be 0 to 9, A to Z, and capital A to Z. And so these are, 62 characters in total. And so 7 characters, 62 base encoded, would result in, 3.5 trillion URLs. And so we do not hit this problem. So 62 to the power 7, which is equal to 3.5 trillion URLs. So basically, by having a short URL of 7 characters and base 62 encoding it, we will have 3.5 trillion unique URLs, which is pretty big number, and that will satisfy our requirements. And so we basically generate a number which is like a big int, and so this has to go from one all the way to 1 billion, or like, yeah, 1 billion. So that's how. So all we have to do is generate a number, and so we have to auto increment it, and then we base 62 encode it. And base 62 encoding, basically what it looks like is, so let's say you have 11567, and so you would convert it, and so this would become 2tx, basically. And so that's how base 62 encoding will work. Um, and so this will be my short URL, basically, that we will return to the user, right? And so this actually works out well, but then the problem is, like, how would you generate an IDE? And so there are various ways to generate an IDE. There is the Twitter Snowflake example. There is, the easiest way that I could think of is, so you have a Redis, and then, you use an INCR, which is basically just Redis returning like the next counter. So the Redis returning a counter to you. And so the Redis will keep returning a counter to you every single time you ask it, so 1, 2, 3, 4, 5, 6, and so on and so forth. And so, you would get that number, and then you would base62 encode it, and, the URL, you can save it in the URL table. And so that's how, our writes should be within 1 second, because all you have to do is, base62 encode a number, and then boom, you enter it into the database, and pretty much done. Now let's talk about scaling the system upon the surge of traffic, like so 50 million users daily. So, this would involve a lot of things. The first thing it would involve is the reads. And so, given that, we're reading from the cache, and the cache is lightning fast, and so basically lookups into the cache are like within a few nanoseconds, because all of this is in memory, and so, our reads are already pretty fast. And then, even if we have to read from the database itself, it's like a log n lookup. So that's pretty fast as well. One could argue that, given that the write service is writing to this database and the read service is reading from this database, like that could be a problem. And, if that's the case, like, yes, the database could be partially locked, given that, one of these services is writing to this database. So the scale of the write is not heavy. It's like 10% of usage. But at the same time, it's always a good practice to have a replica. And so this would be, a master-slave relation, although those terms are outdated now and we don't use them anymore. And so this would be like a primary, secondary, so this would be like a primary secondary relationship. And so, all the reads would then go to this database. And then these two would always be in sync. So every time, the data inside the database is changed, what happens is, it takes the commit log, or sorry, it reads like the change log of this, the master, the primary, and then, the replica actually replicates. The read service reads from the replica, the write service writes to the master. And so that is one way of looking at it, like, further speeding it up, and scaling it. At the same time, the read service will have multiple clients. And so, given like we could just scale it, so we would horizontal scale all of this. And so the way this works is, you would actually specify that as soon as, so, we're using a modular system like Kubernetes, and so you specify as soon as my memory hits 70%, scale up another service or scale up another service. And so based on that, your read service, you have like multiple read services. And so, this would just work out pretty well. Here, at the same time, let's look at the write service. So the write service is also stateless, and so we could have like another write service here, basically. And so, in case of like looking up the Redis cache for an increment counter, that also works out really well, because Redis is single threaded. So, we do not hit any concurrency issues within the system if we scale up our write services as well. One thing, that could be a problem is that, this Redis could go down. And if that's the case, we could have the Redis in a Redis cluster, or like a Redis in, a high availability mode, which is basically a cluster. And so it maintains, a replica. So the same as the database itself. So, our Redis would maintain a replica, and then it would look at this replica, and make sure that, things are working fine here. And so as if, at all, like we have a partition within this Redis master, the replica would like just pick up from where the counter left off. At the same time, we also don't want to bottleneck our services based on the counter. And so what could happen is, the service itself could pick up like the next 1,000 counters, and then this service could pick up the next 1,000 counters. And given that we have 3.5 trillion URLs, it wouldn't matter if we miss a few counters. At the same time, there is also another approach, which is like the Snowflake Redis approach. Sorry, the Twitter Snowflake approach, which is basically this write service could itself generate a number. So it could generate like 4,096 numbers within every single millisecond. And so that's pretty easy to do as well. Like, so you would have a 64-bit integer, so it would generate a 64-bit integer. So some of it would be the timestamp of today, the data center ID, the machine ID, and then, there are 5 bits for it to auto increment. And so every millisecond, every machine can generate a random number or can generate a unique number. And so once you pay 60 to encode that number, you could easily use it for your purposes. And so we are able to scale the system as well. And now let's look at like highly available. And so this system is, if you look at it, it's pretty high availability. So there's fault tolerance written everywhere. So your database has a replica, that's making sure that if the master goes down, the replica takes over. The Redis has a replica so that, if this goes down, your services have multiple replicas, your read services have more replicas. So everything's great. So there is, I do see one possible situation where, our clients. So let's say we have a client and he's constantly hitting our service. So we have a malicious user, or we have like a heavy user, or we have a user who's pretty aggressive, who's pretty using our system pretty aggressively. And so to make sure, like, our API gateway offers us pretty cool stuff like rate limiting, and so service routing, and so load balancing, etc. So, given like all of that, like we will be able to ensure like that we're highly available. At the same time, if we use something like Kubernetes, these are deployment objects, and so they're basically preceded by a service object. Um, and so the service object basically does the load balancing for us. And so, this request will go here, and then, the service object will then send this request to our deployment objects, et cetera, et cetera. So, that will also be helpful to ensure, high availability, and same for the right service, like we will be able to balance the load itself here. So yeah, that will help us with the availability. At the same time, it's always a good practice. Like, I think it's always a good practice to have a region failover. So it's always a good practice to have some sort of resiliency against like a whole region failover. And like, to do that, what we will do is, so this whole setup could be replicated in another region. And so the users would be geo routed based on like whichever region's healthy. So based on where they're located, and so the region that is closest to them, like that would get the request. And at the same time, we do want to make sure that if one of the regions goes down, then we route them to a different region, and so that would make our system like highly available. At the same time, I do want to talk about like a very important aspect that was not in these requirements, which is like monitoring and observability. So like, given the complexity, and this I'm speaking this from my personal experience, given the complexity of the systems these days, I think it's very important to have good observability and monitoring systems in place. So, which is basically to say that the health of each and every single component within this system should be monitored at all times, and we should have automated alerts should one go down. So I mean, the best would be that you have automated rollbacks. You would have automatic deployments if one of the pods go down. But at the same time, we're also monitoring, because there are scenarios where the system's not smart enough or it's not able to handle the scenario where it should automatically come up. So for example, like using Kubernetes, what it offers us is, like as I mentioned, horizontal pod auto scaling. So if one instance of the right service has low memory or low CPU, the autoscaler would automatically spin up a new pod, which is basically to say it will spin up a new instance of the service, and then your Kubernetes service object will start routing traffic to the new pod that was just deployed. So those kinds of things are available, and so to improve our monitoring and observability, what you would have here is you would have a Prometheus server running within your cluster. Prometheus server will be running within your cluster. And so, the Prometheus server is basically talking to your kube state metrics. And so, it is talking to your kube state metrics. It is talking to, your node exporter, and then it is talking to your kubelet. And so what is happening is, it is pulling metrics and data from all of these sources. And so it is then reporting it or saving this within a database. Um, and so, and then, you write PromQL queries to actually query this database. Yeah, and so and then these would be available in a Grafana dashboard, so one could see them in within a Grafana dashboard, and so that is actually pretty cool. Yeah, and so let me just note that down here. Prometheus time series database, right? And so this is a Prometheus time series database. And so, it's at all times it is reading this and showing this here. And then, we also have a Grafana UI that is built on top of this time series database. And then, we have an alert manager that is reading the data from this time series database. And so, that's just like great to have. That's something that's nice to have. Okay, so this is where I conclude my interview formally.